So they won't use the word insoluble because that is not the case. Everything is a little bit soluble. So that's what this chapter, chapter 16, is about. Those things that they don't dissolve very much. Most of you just see fall to the bottom of the container and it's like nothing happened. But something does happen. It's just on a very minor scale. Solubility equilibrium. So we have a whole chapter on that. How can we spend a whole chapter on it? Well, you'll see. You'll see. Here are 3 definitions. We'll talk about solubility and the solubility product Ksp. But I'll just give you a second to write those down. It was there? Yeah. Right where you left it?
No, it was in the office.
Oh. So up at the top of the screen, we see this reaction. A solid is breaking down into aqueous components. This process is called dissolution. Dissolution. That's not disillusioned, Elena. Dissolution. Got that? See the difference between the two? Not the same thing. So the point at which this process happens and then comes to equilibrium, when it comes to equilibrium, that means the reaction is done. And that means that the solution has become saturated with this solute. It's saturated. If it's not saturated, then it's going to continue to dissolve. But the point at which it comes to equilibrium means that XY has become saturated. So yeah, we'll talk about what solubility means. Now the Ksp, we have yet another K. We've seen Keq, which is a general equilibrium constant. Then there's Kw, Ka, Kb. Now we have Ksp in this chapter. Sp stands for solubility products. So when you have this reaction at equilibrium, the Ksp would be the products over the reactants. But the reactants, remember, there's one reactant, it's a solid. So it does not become part of the Ksp expression. We just have that times that, just over 1. There's nothing on the left side that contributes to the K value. So we'll see this a lot in this chapter, the Ksp. What I'd like to do is I have 3 example problems. I'll go through the first one with you. Then the next 2, I'll have you try. And I'll have one little thing after that, and then we're going to call it a day. So let's get at this. Again, I'll go through this with you. If you'd like to copy the question, I'll give you a second to do that. And just look at the question, see if you can digest it. A lot of these questions kind of get at the relationship between the term solubility and what the Ksp is. Those two are not the same thing. So just some basics about these solubility problems. We always write the chemical equation like this. No matter what, I want you to write the equation like this, where the solid is on the left and it's dissolving. The ions are on the right. For no reason do I want you to ever turn that around. And there will be times that you're tempted. Because sometimes there's going to be the question, will it precipitate form? So you're going to have concentrations of the ions, and you want to know if they'll combine together to make a solid. You're going to want to have that thing turned around, but don't. Always write the dissolving chemical equations with the solid on the left. I'll remind you of that when the time comes. Okay, now at the beginning, for almost every ion, we'll always start with 0, unless you have already, like this is trying to dissolve into a solution of calcium chloride or whatever, there's calcium ion. But just plan on, most of the time, the initial concentrations of the ions being 0. Now, some of this solid at the beginning is going to have to shift right, because we can't end with 0 of anything at equilibrium. So it's got to shift right. Some of this has to dissolve. Not much is going to dissolve because it's one of those slightly soluble substances, but some will dissolve. So it's going to go down by some amount. This thing right here, the amount that the solid changes and actually shifts away, that's what we call the solubility. Now in this case, we know what the solubility is. A lot of times we won't. And if we don't know the solubility, we just call the solubility X, like we usually do. How much does it shift away? But in this case, we know what the solubility is. The solubility is 4.8 times 10 to the negative fifth. So that's the amount. Oops. I just lost my board. And I don't think there's anything I can do short of logging it off and back on. Okay, so I'll do this in a moment. This goes down by 4.8 times 10 to the negative fifth. That's how much of it dissolves. That's what the solubility is. And therefore, this and this both go up by 4.8 times 10 to the negative fifth. So the question is, what is the Ksp? I'll just put it over here. The Ksp value would be calculated like this. The concentrated of, it's just the equilibrium constant. The calcium times the oxalate, C2O4, just over 1 because the reactant is a solid. Only gases and aqueous go into decay. That's it. So we know both of those. It's going to be 4.8 times 10 to the negative fifth squared. Which, if this was a multiple choice test and you didn't have a calculator, would you be able to come up with a multiple choice answer for it? Yes, easily. Isn't that close to 5? You know what 5 squared is? 25. Yeah. You know what 10 to the negative fifth squared is? 10 to the negative 10th. Yeah. It's just a little bit less than 25, right? Because it's 4.8 squared, not 5 squared. So it's like 2.3 times 10 to the negative 9. Shane, I'm just looking at Shane's expression. He's like, no, I can't do this. We know, Shane, you can do it. Anybody have any questions about that? It's pretty easy. That's not bad. They're not always this easy. But at the beginning, at least to get us kind of thinking, the main thing about these first 3 terms is the relationship between solubility and the equilibrium constant. Remember, and sometimes that gets fuzzy. Those are not the same thing. The solubility is the amount of the solid that dissolves. That's the solubility. The Ksp is the equilibrium constant at equilibrium, where you take the products and multiply them together. It's going to be divided by 1 for all of these. Okay, now the next one, I'm going to have to restart the computer, but I can put that up there. I'm going to ask you to see if you can try this problem. See if you can get through it. You'll have to fill out the ice table. And while I restart, I'll ask you to try that. And go ahead and talk to the people around you if you'd like to.
Oh.
You're in a race with the computer, whether you know it or not, and I think you're winning. The computer is still trying to restart. Let's try to bring up this file again. And this presentation program, I love it, but man, does it take a long time to load.
Yeah, but you're given the agent concentration thing, so you divide by 2, so you multiply.
Did you consider the coefficients on your ions? You have to, in this case. This is going to wind up, still waiting for that thing to come back up. This is going to be 2.2 times 10 to the negative fourth, the change. Starts at 0, it goes up by 2.2 times 10 to the negative fourth. This one goes up only by half the amount that goes up. So this is 1.1 times 10 to the negative fourth. It's a 2-to-1 ratio. You get 2 of these for every one of those.
Oh, do you have to square the?
You have to square the 2.2 times 10.
Oh, okay. There's code.